So today I'm going to be showing you the floating forks experiment and show you why it's physics, not magic, that makes the forks supposedly float. So to start off, you're going to need 2 forks, glass moderately full with water, and a toothpick. Alright, so you're going to start by taking your 2 forks and placing them together so that they form a crescent shape, connecting the tines, wedging it in there. It's that crescent shape that's going to come in key in the next step. So once you have that, you're going to take your toothpick and stick it in the top slot until you have it moderately balanced on either side. Then you're going to go and balance it on the edge of the cup until it stays still. And there you have it. As you can see, the forks are supposedly floating outside the cup. Crazy, right? Let's go a step further. Grab a lighter and light the end of the toothpick. Even though it's probably pretty obvious, the counterweight of the toothpick is not providing the force necessary to keep the fork system balanced. This goes further to show that it's really just that point right where the toothpick meets the glass that matters. As you can see, it's still balancing perfectly on the edge, with just one point of contact. To calculate the actual physics behind it, I decided to build it on a bigger scale. The center pole resembles the toothpick, and the outer pole serve the purpose of the forks. I began by screwing together the frame and came up with the structure. I'm going to be balancing on my basketball hoop, so here's a test check of how it works. As you can see, it's perfectly lined up right where the center of mass would be. That's key. I hammered in some nails equally spaced on either side to hold some twine in little buckets that I'm going to fill with water. This is what it looked like when I was done. I put exactly 250 milliliters of water into each bucket. I marked where it touched the basketball hoop, since this is the center of mass of the system. Then I disassembled the frame and got some values on the masses. 0.75 kilograms is the average. I did the same with the buckets and got the average. This is the center pole. Now it's time to do some calculations. Here's my schematic of the drawing. I labeled the center masses of each of these points, and then labeled the vertical distance from the top that they would take up. Since it's a 45-degree angle, I could use the cosine of 45 times the hypotenuse. The x's represent the cup of water, and the dots are the center masses of each of the wood pieces. Looking at it from the back view, we can see that since all the weights are equally balanced around the axis of rotation of the center pole, there's zero torque, and the center of gravity from this perspective is right there. Then I calculated the masses and weights of each piece, making sure to double those that were on either side for my side view analysis. For the volume of water, I used rho equals m over v, with rho being 1,000 kilograms per cubic meter. That got me the mass of the water and the weight. Then I put it on a handy-dandy table for the next step. The can and the water are combined since they're at the same place. Here's my free body diagram of the side view. Those are all the weights of the woods and can and water combined, and the other force, but we don't know where it goes since we haven't calculated the center mass. Center of mass and center of gravity are equal in this instance. So to calculate them, those are the equations. I'm going to use the values from the table. These are the values plugged in. Let's solve. We end up getting 0.4095 meters, which is right there. That's the center of the mass of the system, so that should be where the center pole rested on the basketball hoop. That means that all the weight is countered through this point, putting in equilibrium. That also means that the center of mass is there, so we're going to put that symbol there. That's where the center of mass is for the structure as a whole. About 16 inches. Let's see if we were right. So let's measure it up. 16 inches from the top. Perfect. When we draw a free body diagram, we use the center of mass as a singular point from which we draw our arrows going into or out of, representing the force vectors. As we can see through this experiment, that's not just an idealization, but actual physics. As long as you can position the fork system or the system I built exactly on the center of mass, it'll stay balanced in equilibrium. The forces and torques on either side stay balanced, meaning that while it looks like it's floating and defying the laws of physics, it's really just a simple center of mass problem.